So about now, you're probably thinking, this flipped classroom is kind of crazy. All I'm doing is sitting here listening to all these videos. But in fact, what this is allowing us to do is to get through some of the quick and easy stuff so that in class we can do other extension kinds of ideas. The AP exam really focuses on those important extensions and not on the basic nitty-gritty things. They assume that you already know that. So in Chapter 2, we're going to kind of go through these quickly because you already know these. And then we can do some other thoughtful questions in class. So part of Chapter 2 deals with the laws and theories about the atom, and there are some important laws. The first one is the law of conservation of mass. Mass can't be created or destroyed, and of course that's why we have to balance equations essentially. Law of definite proportion says that within a compound you always have the same proportion of elements by mass. So in H2O there was always the same amount of hydrogen and the same amount of oxygen within that compound. The law of multiple proportions, however, compares two different compounds, and you can see the official definition here on the screen, but essentially it says that within two different compounds, they can be made of the same elements, they have a different ratio by mass. Dalton's atomic theory, of course, is very important, 1808. Each element is made up of tiny particles called atoms. The atoms of a given element are identical. The atoms of different elements are different in some fundamental way or ways. Chemical compounds are formed when atoms of different elements combine with each other. A given compound always has the same relative numbers and types of atoms. And finally, chemical reactions involve reorganization of the atoms, changes in the way they are bound together. The atoms themselves are not changed in a chemical reaction. So, which of the following statements regarding Dalton's atomic theory are still believed to be true today? Elements are made of tiny particles called atoms. All atoms of a given element are identical. A given compound always has the same relative numbers and types of atoms, or atoms are indestructible. Hopefully you know that we still believe 1 and 3. Elements are made of tiny particles called atoms, and a given compound always has the same relative numbers and types of atoms. Here are some other scientists, Gay-Lussac and Avogadro. I'm sure you're familiar with these people from our introductory textbook, especially Avogadro and Avogadro's number. Gay-Lussac measured gases under similar conditions of temperature and pressure and saw how they reacted. And Avogadro said at the same temperature and pressure, equal volumes of different gases contain the same number of particles. And that, of course, would be 6.02 times 10 to the 23 particles and would hold a volume of 22.4 liters. But that's coming up in a future chapter. Early experiments to characterize the atom, the famous Rutherford experiment, and explained the nuclear atom. And the atom itself has a dense center of positive charge called the nucleus, and the electrons are light and travel around the nucleus at a large distance around it. In fact, if you look at the picture, it's coming. Electrons, protons, and neutrons, of course, are the subatomic particles within the atom. But if we look at the nucleus, it is small compared with the overall size of the atom, and that's why Ernest Rutherford thought the atom was mostly empty space. It's extremely dense and accounts for almost all of the atom's mass. Here's a picture of it, and you can see that, relatively speaking, the nucleus is very much smaller than the radius or the diameter of that particular atom. In fact, the nucleus is about 10,000 times smaller than the entire atom itself. You should be familiar with isotopes, of course. These are atoms with the same number of protons but different number of neutrons. And they have similar properties, and the difference is the number of electrons. In nature, most elements contain mixtures of isotopes. Here's an example of two isotopes of sodium. You notice that the nucleus of the one on the left has 11 protons and 12 neutrons, and the one on the right has 11 protons and 13 neutrons. They both have 11 electrons. And we would say that sodium 24, which is sodium with a mass of 24, is heavier than sodium 23. Notice how the shorthand notation for writing that is listed below the pictures. So with sodium 23, it's 2311 Na, and sodium 24 is 2411 Na. The number of protons identifies the atom. That's why these are both sodium. So let's see what this is. A certain isotope X contains 23 protons and 28 neutrons. What is the mass number of this isotope? So you'll have to think about how you get that. You'll also need your periodic table. And then you'd have to identify the element. This is a very easy, straightforward question, a perfect multiple choice question on the AP exam. So the mass number is 51. You would add 23 and 28 and you'd get 51. You look up that number of protons, which is 23, and it is the element vanadium. Molecules and ions. Of course, things bond together to form different and new compounds. Covalent bonds are bonds between atoms by sharing electrons. And resulting collection of atoms is called a molecule. So the word molecule often refers to those covalent bonds. Chemical bonds, of course, can be ionic, and that's due to the force of attraction between oppositely charged ions. What we had said in intro was usually ionic bonds involve a metal and a nonmetal because they're far apart on the periodic table, and they tend to be ions, and that's what causes this force of attraction. An ion is an atom or group of atoms that has a net positive or negative charge. You know you have to memorize the polyatomic ions. So is true about the most common ions on the periodic table. A cation is a positive ion, and an anion is a negative ion, one that has gained electrons. So you will see those terms. Here's an example. Certain isotope X plus contains 54 electrons and 78 neutrons. What is the mass number of this isotope? And you can see it's 133. Think about how you would get that number. Remember, if you add 78 and 54, you might not get 133. So think about how they got 133. Other things that you remember, hopefully, from intro is the periodic table, metals and nonmetals. The metals, of course, are on the very far left of the periodic table. The nonmetals are on the right. Groups and families. These are the columns of the table, and they have similar properties, and they have the same, often the same ionic charge. And the periods are the horizontal rows of elements. Here it is in pictures. You can see the family names, mostly alkali metals, alkaline earth metals. Halogens and noble gases are noted here. Transition metals are in the middle. And then the rare earth elements are pulled out at the bottom. In general, these are some common charges. Group 1 has a positive 1 charge. Group 2A has a positive 2 charge. The halogens have a negative charge, and the noble gases have no charge at all. In general. Now, that isn't always true, and we'll talk more about that in class. So we're going to name some simple compounds, and your textbook really breaks it down into very small details. But in our intro class, we did a broader discussion of this, and I'm going to kind of keep it simple. We talked about binary compounds. Those are those that are composed of two elements, and ionic and covalent compounds can be binary. Binary ionic, obviously, is a metal and a nonmetal. It involves ions. Binary covalent are two nonmetals. And that's the way we talked about it. So here's an example. KCl is potassium chloride. Remember, you change the negative ion to end in IDE. Magnesium bromide, MgBr2. because magnesium has a +2 charge, bromine has a -1, and then you have to cancel the charges to have an overall charge of 0, and that's how you get MgBr2. And calcium oxide, CaO. Calcium is a +2, oxygen's a -2. That can be reduced before the compound is formed. Okay, here's another example. And I'm not going through all the rules, which you can read in your book and certainly ask about in class. Here we go. CuBr, copper 1 bromide. Sometimes we need to have a Roman numeral to represent the positive charge. Copper has more than one positive choice, and therefore you need a Roman numeral. In this case, it's a +1. FeS is iron 2 sulfide, because iron is a more than one positive choice, and +2 is the charge of iron in FeS. And finally, here's lead 4 oxide. Notice that lead also has more than one positive charge and needs a Roman numeral when named. Going the other way, here's some polyatomics. You do have to memorize these polyatomics, and I have it in your initial packet, and it's also on table 2.5 on page 62 of your textbook. Here's some compounds containing polyatomics. Sodium hydroxide, magnesium nitrate, ammonium sulfate. These are all that you should have been able to name in the intro class. So this is just refreshing your mind about what to do. Notice some of these polyatomics have parentheses and a number outside, and that is because of the charge of the either anion or cation that it was put with. Sometimes we use the prefix naming system, and here are the prefix names: mono, di, tri, tetra, penta, etc. And it indicates the number of the subscript, essentially, when you use that naming system. Binary covalent compounds. CO2 is carbon dioxide. Now you can use, this is the prefix naming system. You can also use the stock system, as it's called. This would be carbon with a Roman numeral 4 oxide, or carbon dioxide. SF6 is sulfur hexafluoride. And this one, dinitrogen tetroxide. Again, this only works for binary covalent compounds. It cannot be used for ionic compounds, and it cannot be used with a polyatomic ion. So limited use, but certainly easy to do. And finally, acids. This is a whole discussion of acid naming that you can use your old textbook to figure out. They can be recognized by the hydrogen that appears first in the formula. If it starts with H, we're going to assume it's an acid. And it's a molecule with one or more hydrogen ions attached to an anion. So, and this is your book's discussion of it. If the anion does not contain oxygen, in other words, it's something from the periodic table, the acid is named with the prefix hydro and the suffix -ic. So HCl is hydrochloric, HCN is hydrocyanic, H2S is hydrosulfuric. CN is cyanide, which is a polyatomic, but because it does not contain oxygen, we actually do not name it a different way. Now, if it does contain oxygen, the suffix -ic is added to the root name of the anion name that ends in ATE. So, HNO3 is nitric, H2SO4 is sulfuric, no hydro here, and HC2H3O2 is acetic acid. It's like acetate with ic at the end. If it does contain oxygen, you use OUS and you add it to the root name if the anion ends in ite. Ite, remember, it means one less. So HNO2 is a nitrous acid. HNO2 as a compound, if we didn't think it was an acid, would be hydrogen nitrite. So ite goes to us. So nitrous, this is sulfurous, and this is chlorous acid. So you really need to know your polyatomics so you can remember how to do all of this, but we will spend lots and lots of time in class with practice. But now that we have this on this wonderful flipped version, you can watch this over and over again, because I know it's pretty exciting, and practice it. And then when we come to class, you'll really have more time to practice it so that you have it really firmly in your head. All right, here's some questions. Which of the following compounds is named incorrectly? So we have KNO3 as potassium nitrate. Pardon me. TiO2, titanium 2 oxide. SNOH4, tin 4 hydroxide. PBr5, phosphorus pentabromide. And finally, CaCrO4, calcium chromate. So we want to know which is wrong. And let's see what the answer is. Titanium 2 oxide is wrong. Okay, titanium must have a positive 4 charge here because oxygen is negative 2. So therefore, it should be titanium Roman numeral 4 oxide. That ends our discussion of this particular chapter. Hopefully you have gained some information and some knowledge so that we can use it in class. Thanks.